Welcome back. So today we'd like to finish our unit on fluids. So our class is going to be hopefully a touch shorter, but we are going to go over two pretty tricky concepts. So let's go through them. The first concept we want to think about is what happens to the flow of a fluid when the area of the tube that it is flowing through changes. The velocity of a fluid is a little different to think about than the velocity of a solid. In a fluid flow, there must be a mass balance at every point through the tube. If the mass of the fluid that flows into a region, that has to be equal to the mass that flows out. If that is not happening, then it's not really a flow. The amount of fluid at some point is increasing, and so it's not a flow. If that is happening, then the velocity or the pressure or something will adjust pretty quickly, and so that mass balance will resume very quickly. So the mass is the density of the fluid times the volume, and the volume of fluid that is entering a cross-section of the tube is the area of the tube times the velocity. So area times distance gives you distance cubed and divided by time. So the area times the velocity gives you the flow in volume per unit time. So to balance the masses, the density times the area of 1 times the velocity of 1 is equal to the density of 2 at 2 times the area at 2 times the velocity at point 2. So if we're looking at a liquid, liquids have a constant density, so it's very difficult to compress them to change their density, so we call them incompressible fluids. Gases, on the other hand, are pretty easy to compress, and their density can change pretty readily. In this situation, we're going to refer to an incompressible fluid, so while a liquid like water is effectively incompressible. If you fill a balloon with air, you can squish it and decrease the volume, while if you fill a balloon with water, you can push like crazy, and you're really only going to break the balloon. The volume of the water will not meaningfully change. That means that the density is a constant as the liquid flows. If the density is constant, then the mass balance simplifies. So area of 1 times velocity of 1 is equal to the area of 2 times the velocity of 2. So what does that mean? It means that if we decrease the area of our tube, then more water must flow through the smaller tube because the volume flow must be the same. It is like when you have a hose and you pinch the end of the hose, and then the water comes traveling faster, and it goes a further distance when it comes out of the hose. So when you decrease the area of a hose, the velocity increases, and if you increase the area of the hose, then the velocity decreases. Notice this is proportional to area. If we give you a diameter or a radius, then you will have to calculate the area. So like if we tell you that the radius doubles, then the area is equal to pi, so 3.1415 times the radius squared. So if the radius doubles, then the area will increase by a factor of 4. Okay, so we have a problem to do here. A nozzle with an area of 0.4 centimeters squared is attached to a garden hose with an area of 2 centimeters squared. The flow rate through the hose and the nozzle is 0.08 liters per second, and 1 liter is equal to 1,000 cubic centimeters. We want to know what is the velocity through the hose. Well, the flow rate, or volume per second, is equal to the area times velocity. So we have to be careful here because of units. It is probably easiest if we do everything in centimeters here. So first we want to convert liters per second into centimeters cubed per second, since we want an answer in centimeters second. So 0.08 liters per second times the conversion factor, 1,000 centimeters cubed per 1 liter, gives us 80 centimeters cubed per second. Next, if we know the flow and the area, so we want to solve for the velocity. So the flow is equal to the area times the velocity. So the flow is 80 centimeters cubed per second. That's equal to 2 centimeters squared area times the velocity. So we divide the flow by the area to get the velocity, which is 40 centimeters per second. So now we want to know the flow through the nozzle, which has a much smaller area of 0.5 centimeters squared. So now we want to know the flow. So our intuition should tell us that because the nozzle is smaller, more water needs to flow through the nozzle to balance the mass. So it's like when we pinch the hose, the velocity should increase. We can do this one of two ways. The first is to do it just like the first problem. So the flow is equal to the area times velocity. So The flow is still 80 centimeters cubed per second. The area is now 0.5 centimeters squared. So we divide by that to get the velocity. And so when we do that, we get a new velocity of 160 centimeters per second. Okay, so we also could have checked and seen that the area has decreased by a factor of 4, so from 2 centimeters squared to 0.5. If the area decreased by a factor of 4, then the velocity should increase by a factor of 4. So you could just multiply the 40 centimeters per second by 4 to get 160 centimeters per second. Okay, so it's your turn. So you have a few problems about how changing the area changes the velocity of a liquid.